Unit 5, Lesson 2, we're talking about candidates test and the extreme value theorem. Pretty important lesson, actually. We'll develop it as we go, but candidates test is a huge AP exam question. All right, so by the end of the day, you should be able to tell me if the extreme value theorem can guarantee us the existence of an absolute min or max. We talked about how functions typically will have an absolute min or max, but there's circumstances where that could get ruined, like if there's a hole or an asymptote or something like that, or if it just kind of keeps going up forever. That could ruin it. So the extreme value theorem is a theorem that says, hey, there is an absolute max or a min if these conditions are met. Okay, so we'll look at that. So you should be able to look at an equation and tell me, yes, it'll apply here. Next, we're going to use the candidates test. So if there is an extreme value, then the candidates test can be used to find out what those extreme values are. Okay? So that's what we're looking at today. So here's the extreme value theorem. All that's required is that the function's continuous and the endpoints exist. That's it. So continuous, there can be no holes, gaps, or jumps in your function, and the endpoints have to exist, hence the brackets. So you can't have holes on the endpoint. If you have a continuous function and no holes on the endpoints, then there has to be a highest value and a lowest value somewhere. That's what its promises us. So if a function has a global, also known as absolute, min or max, where will it be located? It's either going to be located at the endpoints, like in this case, we have an absolute max, or it'll be located at one of the relative extrema, like this. That's not an endpoint, but that's like one of those relative extrema. So that, in this case, the relative minimum is also an absolute min, or a global min. So global extrema are located either at the endpoints or at the relative extrema. All right? So how do we use the candidates test to find the absolute min or max? Well, this looks like a lot of steps, but let me just kind of try to make it a little bit simpler before I get into the details. First of all, you want to make sure they exist. Do they exist? Second of all, we're just going to look at the endpoints and the relative extrema and see which one of those is the biggest and which one's the smallest. That's it. Now, we're not going to be looking at graphs today, though. We're going to be looking at equations. So here's how we'll do it. So first of all, we'll verify that there is a absolute min or max. In other words, does the extreme value theorem apply to this? You can tell so long as it's continuous. In other words, no holes, gaps, or jumps on the interval. And it's closed interval. In other words, the endpoints are included. All right. Next, we'll find these next steps here. These next steps here are for finding the critical values, which are possible relative extremes. All right. So we're going to find the derivative and set it equal to 0. And we're also going to see where is the derivative undefined. Remember, if you have a relative max or min, it looks like this. That's where the derivative equals 0. If you have, or it could look like this, in which case your derivative would be undefined. So we're going to look for the places where the derivative is undefined and equals 0. Those are the relative extrema. Okay. Once we know where all those values are at, what we're going to do is we're going to make a chart. I'll put this together here, and we're going to make a chart. You're going to put your endpoint in a chart here, your first endpoint and your last endpoint, and you're going to put all your critical values in there that you found in steps 2 and 3. And the last step is to plug everything in and see which one gives you the biggest y value. The biggest y value will be the absolute max or min. Yeah. Oh, so today we're not having graphs. Now I put them on your notes today, just so you can like compare our algebra with the picture, but typically you won't have a picture to go with it. So this is called this whole process here really, but that chart in particular is called the candidates test. That's a really important thing to know how to do. A lot of times on the AP exam they'll say justify your answer. this is the only time where one of the only times where you don't really have to write a sentence to explain yourself. If you wrote this chart out, that is your explanation for why the max is the max and why the min is the min. Just so you know. So that I would add this to your notes here if you haven't already, and just know that that's the candidate test right. That's an important piece. The E stands for endpoints, and the C stands for critical values. The endpoints are kind of obvious because they give them to you. The critical values are the things that you find in steps 2 and 3. So while you're writing, I'll just keep talking, but just to remind you, we're looking for absolute min and max. Where are they located? Either the endpoints or at the relative extrema. We put those things into a chart and we see which one actually comes out to be the biggest. But we do have to begin, though, to make sure that they actually exist. You'll see there's some situations where, oh, you know what? We can't be really sure that exists. So you would actually stop and just say, we're not sure.
Right, we're not sure.
Oh, we'll see some examples. I'll be more specific when we get there. So why do we care about this kind of stuff? Like, I put a scenario in here, but you guys can imagine any time, like in the world of engineering or design, you usually want to maximize or minimize something, like maximize your profit or something like that. So finding mins and maxes is very useful. So, it's always had a purpose. I just don't focus on it a lot. I like math for math's sake. I'm not a big app guy. All right. Let's go ahead and take a look here. Example 1. Find the absolute min or max of the given function on the specified interval. All right, so I'm going to use this as a guide here, my steps. So I'm going to number my steps just like they are here on the problem we're working on. Okay, so step 1, does the EVT apply? Okay, well, first of all, I'm going to see if it's continuous. What do we call this kind of a function? Polynomials. Where do polynomials have discontinuities? Don't. Good. So we're going to say yes, and polynomials are continuous everywhere. We also want to make sure that we have a closed interval. Do we have a closed interval? Yes. Yeah, if we got brackets, so that's a good thing. All right, moving on, number 2.
I got a question.
Yeah.
If it was not continuous or if it was in brackets, then you just need to stop it.
So, yeah, so that's a good question. You would not be sure it doesn't exist if it's not continuous. Now, I will give you guys some situations where there are not brackets there. What that will end up doing is it will end up getting rid of maybe a minimum or a maximum, but we'll still look for them. But if it's not continuous, then without a picture, it's kind of difficult to tell where the max would be at. So let me summarize. For here, you pretty much kind of have to stop if it's not continuous. You're not going to know for sure. But if this one doesn't work, we could still mess around with it. You can know if that would apply or not. So we'll see an example. Let's go ahead and take a look at 2. All right, so second step. What was the second step? Remind me. Okay, so we need to find where does f prime of c equal 0. So first of all, let's find our derivative. F prime would be 12x cubed minus 12x squared. And we're going to set that equal to 0. I'm out of space, so I'll continue my work up here. We're going to factor. What factoring method would I use? GCF, box, or difference of squares? Yep, so they do have something in common. We can take out. What can we divide out of both of those? 12x squared. If I take out 12x squared, what would I be left with on the inside? X minus 1. We're going to set them both equal to 0. solve. This one, if you divide by 12 and take a square root, you're just going to get 0. But if you see that and you don't want to show all this work, you don't necessarily have to. This one, so I've got two critical values here so far. I've got a critical value at 0, and I've got a critical value at 1. I've got a critical value at 0 and a critical value at 1. All right, so let's move on to step 3. We can possibly find some more critical values if we find where the derivative is undefined. So here's my derivative. That's a polynomial. Is that ever undefined? No, because they're continuous everywhere. So since the derivative, which is 12x cubed minus 12x squared, is a polynomial, it is never undefined. In other words, there's no cusps on this thing. Polynomials are always smooth. They don't have cusps. So you'll never have an undefined critical value on a polynomial. All right, so we found all the possible critical values that we can. So now we're ready for step 4. What does step 4 say? Okay, so this is where you do the chart. And this is probably one of the most important things to write on an FRQ is this chart thing here. So, all right, now a little word of advice. As you're doing this, it's possible that, you know, like let's say that I'm talking about a function that looks like this, right? But they only want me to look on this interval here. So in here only. So it's possible that on step 2 or 3, you'll find a critical value, like that's a critical value, but I don't care about that one because it's not in the interval that I care about. Does that make sense? So you got to be careful not to include them because in this case, based on that picture, you guys see that this one would have come out to be our max, right? But if it's not in the interval they don't care about, then you're going to get the wrong answer. So here's how you can avoid including critical values that you don't want to include. Always start by putting your endpoints in there first. So my endpoints are -1 and 2. I'm going to put -1 here, and I'm going to put 2 here. And then after you put in your endpoints, put your critical values in only if they're actually in between there. Is 0 between those two values? So I'm going to put it in there. How about 1? So I'm going to put it in there. If I had another critical value, like let's say it was 3, you would not include that. If you did, you'll find a max, but not on the interval they care about, and you're going to get the wrong answer. Now we got to find our y values. To find your y values, you're going to plug them into the function here. And after that, we'll see which one's the biggest and which one's the smallest, and there's your max and min. Now, if you want to get a calculator at this point, you can. I'm going to use a calculator to do this. So if you want to get a calculator, you can. I don't want to plug these numbers in by hand. So I'm going to just use a calculator. So if you want to grab one, if you don't remember how to plug it in, then I would recommend getting a calculator. If you feel like you remember, then cool. I'm going to use the whole thing where I plug it into the Y1 spot, and then I'm going to do the bars thing. So I'll walk you through it again if you want to practice. So here we are. What is the absolute minimum? That's the smallest number. So let's label that. And by the way, this is step 5. So I'll put 5 here. And then this is the absolute max. Now, I think I put the picture on your guys' paper, so you can verify that by looking at the graph. But there's your absolute min and absolute max. Okay. Yep, you can write them as points. So Lars asked a good question. How they ask the question will matter how you answer. They might say, at what values of x is the absolute max? Well, they want an x value there. So if they said at what value of x is the max, what would the answer be? Well, the absolute max is at 2, right? If they said what is the absolute max, 16. Sometimes they'll say at what point does the max occur? They want it written as a point in that case. So you got to pay attention to the question they're asking.
So you say 216.
Yeah, that would be a point. So it just depends how they ask the question. All right. And there's our graph. And you guys can see here, there's our max at 16, and there's our, no, that's not our minimum. Our minimum is here at that critical value. Yes.
So do we just leave it as a chart, or do we have to like simplify and say like, oh, the minimum is y?
No, I think if you circled it and put min and max, that would be perfectly fine. Yeah.
Oh, how much points would this be if it was
A lot of times, that's a good question. A lot of times these critical value chart questions are like worth about 3 points on an FRQ. That's a lot because there's 9 points and there's like 4 questions. So in other words, this question makes up like a third of the test. And that means if you just earned like 2 more points somewhere else, you passed that FRQ. 5 out of 9 would be a pass. So these are good questions to know. All right, now I'm going to make a slight change here. You guys ready? Here we go. So you already see it. A lot of the stuff is the same. So I'm just going to put does the EVT apply? The answer is no, and here's why. Because it's not a closed interval. It's not a closed interval. Now, here's the thing though. We could still do the chart. I'm going to skip steps 2 through 3 because we already did this. Everything else, nothing's going to change. If I give you a parenthesis, all these steps are the same. You guys notice it's the same function, right? We're going to get all the same answers. Nothing's going to change. Here's where it will change those on step 4. Suppose I gave you guys step 4 now. We already did all this work also. We had negative 1, 0, 1, 2. This was 7, 0, negative 1, and 16, right? All right. Does this point exist on the graph, negative 1? Yes. Yes, it does. Because I've got a bracket for that one. Does this point exist, 0? Yeah, that was one of our critical values, and we said the thing was continuous, so there should be no holes or gaps or jumps. Does this one exist? Now, does this one exist?
No.
That's where the parenthesis is. So I'm putting open dots and closed dots next to it here. You would still do all this work, okay? But here's the thing. This is still going to be my minimum. This would have been my absolute max, but we're going to cross it out because it doesn't exist. So how would the answer look like for this one, like on a test? You would say this graph has an absolute min at negative 1, but it doesn't have an absolute max. It would have. It would have been at 16, but it doesn't exist, so no good. Yeah.
Okay, so because it's the open interval by the 2, so anything after the 2 is open. Would the new max be 7?
That's a good question. Let me come back to you. You said, would anything after that be? We wouldn't even include anything after that. So we don't even care about anything after the 2. Now, let me go to her and then I'll come back to you guys. Oh, there's Lars. Okay, so now here's the question. This is an important question. It seems kind of intuitively clear to us, but it's not true. So here's the thing. We think, oh, well, this isn't the biggest number, so it must be the next one, 7. No, remember, we're only looking at specific points, right? There could be some numbers between there that are bigger than 7, but less than 16. 16 would have been our max, but it didn't make it. So there's numbers still in there. Let me show you a graph to make it more clear. When we do this chart, we're only looking at the critical values and the endpoint. Here's, oh, did I not have a graph for that one? Okay, so it's the same graph. The only difference is now I've got an open dot here. When we do the candidates test, we're only looking at the endpoints and the critical values. Oops, I think I did that wrong. Critical values here and here. We're only looking at those 4. Now, where's 7? Here's that 7 you guys were saying, right? Do you guys see there's a whole bunch of other points bigger than that? We just didn't look at them because they were not candidates for the max. Okay? So this was a candidate. It failed, but it was a candidate. This was a candidate, and it failed. None of these guys can be a max, but they're still bigger than that other candidate. So no, you don't just go to the next number. It either is the number or it's not. All right, any questions? All right, so I want you guys now to try one on your own. I've got the graph here. You can kind of see the answers already, but I am going to ask you guys to tell me your answers for steps 1 through 5. Okay, so do work it out, show all your steps, and I'll give you a couple minutes for that. Okay, so there is the result for student practice. Now, I'm giving you guys the picture. You can see here's your minimum, and you can see the max, but just know that it won't, I'm not giving you a picture on homework and quizzes and things. I'm trying to help you out a little bit here. Mm-hmm. It's where the derivative would be discontinuous. The original function would not be. The point exists. It's just the derivative would not be. All right. Now, guys, the rest of our lesson today, I'm going to try to get through as many as I can with the time that we have. I might just do all of them after school today and then upload the video then. That way you guys can see other examples, but I want to go through other types of functions and how to deal with those. So polynomials, I like those because they're basic, they're straightforward. The other ones, the derivatives, are a little bit tricky, and we have some things to talk about. So, but what's important here is we have the steps on how to find the extreme values down. The thing that makes these other problems tricky is the derivatives and stuff. All right, so here we go. Let's do this one here. Step 1. Does the EVT apply? Now, I'm not going to have you get it out in the interest of time, but I gave you guys a sheet that tells you where these functions are continuous and where they're not continuous. This function is actually a cube root function. I'm going to rewrite it like this, and I would encourage you guys to do the same. Cube roots are continuous everywhere. They don't have any holes, jumps, or gaps, but it's on that sheet full of functions where I tell you where all the discontinuities are. We've looked at it many times this time. Cube roots are never discontinuous. Now, if it was an even root, it would not be continuous everywhere, so you have to keep that in mind. All right, but with an odd root, the answer is yes, it is continuous. Part B. Are we on a closed? Yes. So there should be a min and a max. All right, let's go ahead and take a look at 2. Now for number 2, the derivative is going to be a little bit tricky. All right, it's going to be a chain rule. We have an outside function here. Yeah. It could go either way. We have an inside function and an outside function. So let's do the outside first. The outside would be negative 2/3. And if I subtract, what is 2/3 minus 1? Negative 1/3. And we're going to multiply that by the derivative of the inside. What's the derivative of the inside? 4. Okay. And we're going to set that equal to 0. A little bit. All right. So, first of all, if I multiply these together, I get what? Negative 8/3. Now, here's another thing to keep in mind. What does the negative exponent do?
It makes it a fraction.
It moves it to the denominator by making it like a fraction. So I'm going to write it like this. Now, when it comes to rational expressions, you guys, if you want to find where they equal 0, you set the top equal to 0. When you have a fraction, it makes it 0 if the top is 0. So now, can negative 8 equal 0 then? So there's no answer to this. So for this one, you set the numerator equal to 0. Okay? That's how you can find where the rational expression is equal to 0. Now for part 4, though, we want to find where the derivative is undefined. This was where f prime was 0. I'll write that. I didn't write that here. So for this one, you set the top equal to 0 to find out where it equals 0. Here, how do you find where a fraction is undefined? I'll set the bottom equal to 0. Fraction is a 0 on the bottom that's undefined. So you can find where it's undefined.
Wait, is that something?
No, I'm on step 4 now. Oh, wait. No, you're right. It is step 3. My bad. Gracias.
I was going crazy.
What is it? 1/3? You set the bottom equal to 0. So when you have a fraction, to find where it equals 0, you set the top equal to 0. To find where it's undefined, you set the bottom equal to 0.
Doesn't matter if it's C, I mean, F, C,
No.
or F, that.
No, I'm just being inconsistent.
Mr. Bailey, isn't there the 3? Yeah.
What's wrong?
The 3.
Oh, thank you, yeah. There is a 3 there. Now, I'm going to say stuff, but in the future, I'm going to do this a little bit easier. First of all, how would you get rid of the 3? You would divide it out. It's just going to go away. How would you get rid of a 3rd? You would raise both sides to the power of 3. But what's 0 to the 3rd power?
0.
So basically, anything except for what's in the parentheses, you can just get rid of it. So in the future, I'm not going to write all that out. I'm just going to set the part that's in parentheses equal to 0, because that's the only part that really matters. So I didn't get any critical values where the derivative was equal to 0, but I did get some critical values where the derivative was undefined. Now, if the derivative is undefined, that could be because it's not continuous, or it could be a cusp. I know this has to be a cusp because I already know this thing's continuous everywhere. So this has to be a cusp. All right, we're ready for our chart. Now here I'm going to have you guys help me out a little bit. So, here we go. Sabrina, what am I putting on the left side? Uh-huh.
Oh, unless it's
Yeah.
2 and at the bottom it's gonna be 8.
Uh-huh.
And then in the middle no answer.
There it is. It's just in a different place this time. It's 4. It was from step 3. We got x equals 4 as one of our critical values. All right. At this point, would you guys calculate these for me? Thank you. I appreciate that. That's so nice. All right. So there's that one. And there's our picture. I want to get through as many as I can. Oh, we do? I guess we'll stop there. I will do these after class today, after school today, and then I'll upload it so you guys can see it. This one has, this is a rational expression. This one does have a discontinuity. Okay? I'll show you how to work through that, but there's that. And then here's a trig one. Those are always fun, so I'll just do that for the next one. But anyway, the rest of it's pretty, that's it. So I just wouldn't have time to get to these two today, but I will do a video on them. You know, I would encourage you guys to watch it and complete your notes, but if you don't, it's okay. I mean, I'm not going to check, in other words. I really think you should. All right, so let's go ahead and take a look at the third one here. So first we want to see, does the EVT apply? You will notice that this one is not continuous. And here's why. If you guys look at your sheet for common functions and their continuity that I handed out to you guys last semester, you'll notice that this is a rational expression. And rational expressions have discontinuities anytime the denominator equals 0. So we have a discontinuity at x equals 1, which is on this interval. And therefore, no, the EVT does not guarantee us the existence of an absolute min or an absolute max. Now, we saw before that anytime you have parentheses here, you could just kind of go through the whole process, and if it turns out that your max was on one of the endpoints or your minimum, you just have to get rid of it and not include it. But whenever a function fails to be continuous because there's some number on the interval that fails, in that case, you really can't be sure at all unless you just look at the picture. Okay? Now, I'm still going to go through all of the steps just so you guys can kind of see how to do the steps with this type of a function, a rational function. But ultimately, in the end, right here was kind of enough for us to stop and say, well, I think we probably just have to give up and not look for it. Because as soon as you find that it's not continuous at x equals 1, or some point along the interval, your conclusions are going to be they don't give you good information, so you can't really tell. Okay, but I do want to work it out just so you guys can kind of be reviewing derivatives and things like that. So first of all, let's go ahead and find our derivative. To do that, you're going to do the quotient rule, which is low d high minus high d low. Draw a line and square below. Okay. Now what we have to do is remember how we said that for number 2, if you want to find out where the derivative is equal to 0, then you're going to set the top equal to 0. So it's going to be that. And for 3, if you want to find out where the derivative is undefined, you set the bottom equal to 0. And I just realized, by the way, this was supposed to be squared. But remember, we talked about in class how you really don't need to include anything except for what's in the parentheses when you do this. So Let's go ahead and do the one on the right. That's easier. Now, I end up with x equals 1. Now, that's not actually a critical value. I'm going to cross that off. Here's why it's not a CV. The function is not defined at that point. In order to be a critical value, the function has to exist at that point, and it doesn't. So I'm not going to include that one. So that's something new there. If you ever get a critical value, which is one of the places where your function doesn't exist, then you're not going to include that one. Now let's go ahead and solve this other equation here on the left. I'm going to distribute first. I'm going to combine my like terms. And I'm going to solve this by doing a GCF. If I set this equal to 0 and solve, I get x equals 0. If I set this equal to 0 and solve, I get x equals 2. Okay. So we have two critical values on this interval. We had a third one, but we threw it out because it was a place where my function is not defined. All right. So now we're ready for steps 4 and 5. So we're starting at -1, we're ending at 3, and I had two critical values, both of which are on that interval. And then I'm going to go ahead and plug them into the original function now. Now, the reason why I wanted to go through this problem is because I just wanted you guys to see how to do the derivative and stuff like that. But for number 6, though, we could have jumped straight to number 6 after number 1 because it's inconclusive. The only way you can really tell what your max and min is by looking at the graph here. Now, if you were looking at this table, you might think, oh, well, there's my max, and here's my minimum. But let me show you the graph, and I'll show you why that's not the case. Okay, so this is what the graph would look like. And these 4 points that I have highlighted on this graph are the values, the x values that we found, x and y values that we found in our table there. Now, just looking at the table that we had up there earlier, you might have thought that -1 was an absolute min and 3 was an absolute max. But as you guys can see, that's not the case. As you guys could tell, those are not the highest and lowest points. And the reason for that is because we had that place where the function was undefined, which is right here on this vertical asymptote. And since we have a vertical asymptote, this function never stops going up or down, and therefore there is no absolute max or min. So in general, here's kind of what you can conclude. If you ever have a place where the function is not continuous on the interval, I would say you just can't tell if there's a maximum or a minimum without looking at the graph. Okay. Now, if you ever, if you have a rational expression in particular, anytime you have a discontinuity on the interval, you won't have a maximum min because it creates a vertical asymptote. And vertical asymptotes, the function goes off into infinity. Okay. Now, we saw another situation, though, earlier today in our lesson, and it was this one over here. Let me back up a little bit. This is another place where the EVT did apply, but we had a more solid conclusion in that case. When the endpoints are places where it's not defined, that's okay. We can still do our little table thing. We just have to be careful not to include the endpoints in our final answer. But when you have a rational function where the discontinuity is somewhere on the interval, that means you have a vertical asymptote, and that means there is no absolute max or absolute minimum. Okay, so that's one situation. Now, I did want to go through all, so you really could have stopped at step 1 and you could have just said there is no absolute max or min. However, I did want to work out the other steps just to review with you guys how to do derivatives, how you could tell where the function is equal to 0 and where it's undefined, etc. A lot of good stuff to talk about, so I wanted to go through those steps. But in general, just to repeat, if you ever have a rational function with a discontinuity on the interval, that means there is no absolute max or min, just so you know. Now, those other points that I had up there, I had a point here and I had a point here. Those are relative, sorry, I was at 2. Those are relative extrema, so if I asked you to find the relative extrema, you'd be able to do that. But they weren't absolute extrema. All right, let's go ahead and take a look at another example. This one is a trig example. There's not a whole lot special here. I just want to do it because trig is always, a little bit foreign. So let's go ahead and work this out. All right, so step 1, does the EVT apply? All right, well, cosine functions are continuous everywhere. They don't have discontinuities. And once again, we also have brackets on both ends. So yes, we should be able to find a max and min on this particular function. Let's go ahead and take a look at step 2. We want to find our derivative. Once again, it's going to be a chain rule. We saw one of those earlier today. This is all outside function stuff. And then the inside function would be this 2x here. So the derivative of the outside is negative 2 cosine, I'm sorry, no it is not. The derivative of the outside is going to be positive 2 sine of 2x. It becomes positive because when you take the derivative of cosine, that makes negative, and since we already have a negative, they cancel, make it positive. And then we're going to multiply that by the derivative of the inside, which is 2, and there's my derivative. Now I'm going to simplify that a little bit to 4 sine 4x, and I'm going to set that equal to 0 for step 2. Okay, so dividing both sides by 4 first, we get that. Next, I want to find out where does sine equal 0. So if you get out your trig chart and find the angles for which sine is equal to 0, you will find that sine is equal to 0 both at 0 and at pi and at 2 pi. So there's 3 places on one revolution around the unit circle where sine is equal to 0. That means that 4x can be equal to 0, pi, or 2 pi. If I solve this first one here by dividing by 4, I get x equals 0. If I divide by 4 on this one, I get x equals pi over 4. And if I solve this one by dividing by 4, I get pi over 2. Okay? So that does it for step 2. We'll move on to step 3. But I just, before I move on, just want to point out to you guys that, so what's the deal with the trig one? First of all, I can remember how to do your derivative, which is, that one's not too bad. But what you do is you use your little trig reference sheet, you find out where that trig function is equal to 0, and you set the inside equal to those things. Now technically, just so you guys know, there's an infinite number of answers, but I'm only going from 0 to 2 pi. Because that's what I have on the back of my trig reference sheet. It can go on more, though. We'll see if it looks like enough. But we'll get to that in a minute. For now, we also want to find out where the derivative is undefined. All right. Well, the derivative is a sine function. Sine functions are continuous everywhere. And therefore, there are no there's no places where it's undefined. So we have these 3 critical values. All right, we're ready for step 4 and 5, which is the table. So we're starting at 0 and we're ending at 3 pi over 4. Now, how do I know if these numbers are on the interval? Well, obviously 0 is okay. I've already got it there, so we don't really care about the 0. What about pi over 4? Well, there's two ways that you guys can handle this. One way you can decide if it's on the interval is you could just change this into a decimal. Do on your calculator, do pi divided by 4 and see what you get, and compare it to this, and find out is that between 0 and that number. Another way you could do is you could just think about the shape of the unit circle. Okay, if we're going from 0, that's here, to 3 pi over 4, that's over here in the middle of the second quadrant. So this is where 3 pi over 4 is. So is pi over 4 in there? Well, if you know that pi over 4 is here, yes. As you can see, to get from here to here, we do have to cross pi over 4. So pi over 4 is included in the interval. How about pi over 2? Well, pi over 2 is here at the top. So as you can see, yes, we also cross pi over 2. So that's an option as well. Okay, so we have those 4 values of x. All of them are good critical values to check. All right, the last thing we're going to do is we're going to plug them into the original function. Now what I'll do is I'll work out one of the problems, and then I'll just give you the answers for the rest. And I'll pick one of the harder ones to do. But you could just do it on a calculator once again. But just to review trig, I think I'll go over this with you guys. So let's say I did f of, I'll do 3 pi over 4. I'll do the last one, 3 pi over 4. This one down here. All right, so I take my original function, and I'm going to plug in 2, and then I'm going to plug 3 pi over 4 in next to that for x. So if I multiply those together, I get 6 pi over 4. And 6 pi over 4 reduces to 3 pi over 2. Then I would look at my chart, and I would see what is cosine of 3 pi over 2, and I would find out that that is 0, and negative 2 times 0 is just 0. So this one is 0. All right. I'll let you guys do the rest of them. I don't care if you use a calculator, if you want to use your trig reference sheet. Maybe I would encourage you to try your trig reference sheet on at least one of them, just so you know how to use that again. But for the rest of them, I'll just put the answers up here. All right, so there's our answers. And since we know that the max and min have to exist, I can see that this is the max and that's the min. So once again, I think I included a graph here. The minimum was -2. The max is +2. All right, so there's your other 2 examples. Just kind of remind you guys how to work with different types of functions. All right, so nice job. We'll see you guys next time.